Good day, everybody, and welcome to day 2 of OptiWave's webinar week. We're going to be starting off the day with our Optigrading webinar. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your presenter, Steve Dodds. Before we begin, let's go over a few things. So during the presentation, I'm going to launch 3 polls, such as the one that you're viewing now. And if you are present for all 3 polls, your name will be entered into our $50 gift card draw, in which the winner will be drawn randomly and posted on our website at 10 a.m. Eastern Standard Time today. We will also have 2 question and answer periods, the first one at the halfway point and the second one at the end of the webinar. As in previous sessions, we're not going to be handling questions via the raised hand option, so we ask that you please type all questions into the questions section only. Finally, we're going to be recording the webinar and distributing it to all registrants via download link that you'll receive in an email tomorrow, 24 hours after the webinar ends. So you'll receive it at around 10 a.m. Eastern Standard Time tomorrow. If you'd like to access the recording earlier, what you can do is you can go to the page that you used to sign up for the webinar. Just click the link and it'll take you to the registration page. You can click register again, and then it'll push you right to the video of the recorded session. You will have to give it about an hour to render the video after the session ends, so probably around 11 a.m. Eastern Standard Time today, the video should be available if you take that route. So with all that said, I'd like to now hand it over to your presenter, our Optigrading Product Manager, Steve Dodds.
Thank you, Brian. Welcome to the Optigrading webinar. I'm showing right now what you would see if you were running this software, what you see at the beginning. Optigrading is a software for calculating the reflection and transmission spectra through fiber Bragg gratings. It does this using the coupled mode theory connected with transmission matrix methods. And then when you begin Optigrading, the first thing that it will ask you is exactly what kind of structure have you got. Option 1 is a single fiber, so this means that you have an optical fiber and you have put some kind of grating on it. There are other options. Optigrading can also find reflection transmission spectra in the case of 2 fibers brought close together, fiber coupler. It can also accommodate gratings that are on planar waveguides, or a grating that is found between waveguide coupler grating. There's also a feature of other waveguide. If you use other waveguide, you can do any kind of waveguide, but you're going to have to calculate modal index and overlap integrals and so on yourself. For fibers, Optigrading will do this for you. I'm going to show you a single fiber. So this needs to begin with the specification of the fiber itself. The example shown here is a step index fiber. It's got a core layer with refractive index 1.46. It's got a cladding of 1.45. And one can add more layers to this, and the layers don't have to be constant either. They could be graded index fibers as well. Another datum that's here is the central wavelength. Optigrading is going to make a grading for us, choosing a lot of the parameters by itself. What the central wavelength means is this is where we would like to have the reflectance peak. So in the next dialog box, it's going to calculate the optical mode that would be found on this fiber. It'll use the modal index of that to select what the grading period should be in order to get a reflectance peak at 1.55 microns. It's convenient, done for the sake of convenience. If you don't, if you want peak at another wavelength, it's easy to do that. Okay, so that's what that we specify our fiber. In the next step, we're going to find the modes on this fiber, and we are looking at wavelength 1.55 microns, and it finds one mode, the LP01 mode. Let's have a look if there are any higher order modes. No, there's nothing there. This is a single mode waveguide. But if we use a shorter wavelength, calculate again, yes, a higher order mode appears at 0.8 microns. But we're going to be doing our example near the longer wavelength, 1.5. And for here, this is a single mode fiber. So we've got a fiber and we know what the optical mode looks like. And now it's up to us to specify what the grading should look like. It will make one grading by default. This grading has a length of 50,000 microns and this period and so on. We could put more than one grading here by adding layers. This will put one grading after another. So if that's the sort of fiber you've got, you can make that one as well. But we're going to start just by looking at one grading put on the fiber. Double click on this and it brings up a bunch of details. One detail, as mentioned, is the length. I'm going to make the length 10,000 microns, or 10 millimeters. And we also need to specify what the index modulation should be. A Bragg grading consists of changes in the refractive index of the material in a periodic way as we move down the grading. And this number specifies how the extent of those modulations. So this one will mean that the refractive index gets higher than the average by 0.003 and also gets lower than the average by 0.003. And it does so in a period of 533 nanometers. And this was automatically generated, taking into consideration the modal index of the optical fiber that was just calculated. The grading could be formed by variations that are going up and down like a sine wave. It could be done in other ways, an abrupt rectangle, or something that you specify by file or by some formulas. So that's enough to specify a simple grading. And having specified all of that, we're now in a position to calculate a spectrum, a convenient range to view. This particular spectrum is a little bit lower and a little bit higher than our central wavelength of 1.55. I'm going to add a few more points to the... It goes through, and the blue is the reflection, the reflectivity, and the red is the transmission through this grading. And as expected, we get a maximum reflectivity centered around 1.55 microns. This is a basic grading. We show here a description of how the grading changes along the length of the grading. The grading was 10,000 microns long, 10 millimeters long, and there's no changes to this grading over this length. The variations are very rapid, of course, so we can't show them all, but the refractive index change will be going as much as 0.003 higher than average and as low as 0.003 lower than average. And this doesn't change all the way over the length. But it's been known for a long time that if you do it differently, if you start the grading with a very low, small modulation level and then increase it to become larger in the middle and small again at the end, this can have a desirable influence on the reflection spectrum. This reflection spectrum has a very high reflectivity at the center wavelength, but outside the center wavelength, in what we would like to be passband, we have very high side bands. They're only a few the peaks here are only a few dB down from 0. So this has a lot of transmission in the side bands. And it's been known for a long time that an effective way of reducing these side bands is to apply so-called apologization. Right now it's uniform, we don't change anything, but we can apply all different kinds of apologization. You can even specify it by a user-defined formula. Here is an example of such a formula, and here it is displayed over the 10 millimeters. So what's going to happen here is we're going to start the index modulation quite small at the beginning of the grading. It's going to go up to its maximum level in the center of the grading and then become small again. So we can do that. This number of segments becomes important at this point. As I mentioned, it calculates the reflection transmission spectra by using coupled mode theory. For coupled mode theory, exact solutions are known for the case where the grading is constant. We're going to be apodizing it, making it small, making it bigger. So in order to calculate the total reflection and transmission, we are going to divide that changing grading up into 300 parts. Optigrading will apply the coupled mode theory to each one of these constant parts and connect them all together with transfer matrices to find out what the total reflection spectrum will be. So that's a detail about the calculation. So when the grating is apodized and we calculate again, you'll see what happens to these sidebands. They drop away. They are quite dramatically lower now. And why is that? Well, we look at the grating and, well, it's a different grating. As I said, it turns on the very small modulation at first and then just becoming gradually larger. So that's one thing you can do with a grating. You can apodize it to reduce the level of the sidebands. Something else that people like to do with gratings is to chirp them. The reason for that is twofold. I'll show you one thing that happens. Chirping means that we are not going to use this constant period all the way through the grating. What we're going to do is we're going to change that chirp. We're going to have it, the local period of the grating is going to change over the length, over the 10 millimeters of the grating. It's going to be 2 nanometers shorter at the end of the grating than it is at the beginning. And yes, that does have a significant effect on the reflection transmission spectrum. I'll show you what happens. It might not surprise you to find that the bandwidth becomes larger. That kind of makes sense because now the new grating, we're not able to show the period by actual drawing of period. It's too short. They're much too small. So what we do is use a color code to indicate what the local period is. So at the left end of the grating, the period is 535 nanometers, and then at the right end of the grating, it's only 533 nanometers. So the period gets shorter very slowly over these 10 millimeters. And knowing that, you might not be surprised to find that, yes, indeed, it makes the stop band wider because we're presenting it with a wider range of periods, so that longer wavelengths would like to interact with the longer period. It will reach the quarter wave Bragg condition at a longer wavelength at the beginning of the grating, and the situation is the opposite at the other end. So by contributing over a wider range of wavelengths, it opens up the bandwidth quite a lot. We have a tracing feature too. We can look precisely at what's happening here. So now we've got a bandwidth that starts about 1.548 microns and goes up to 1.552 microns. Something else happens in the chirping of the grating. This is evident when we look not at the power of the reflection. Let's look at the phase of the reflection. It's the blue line that is the phase. Notice that the phase over the wavelength is not a straight line. It kind of bends. And it's well known that the rate of change of the phase of the optical reflection is the delay of a pulse at this wavelength. So the rate of change of this is different at this end than it is at that end. So we expect that the delay of a pulse at one wavelength will be different than the delay of a pulse at another wavelength. And Optigrading, in fact, it actually does calculate this by taking the rate of change of this phase. And yes, indeed, we see that pulse at shorter wavelength is going to spend well close to 100 picoseconds before it turns around and comes back, whereas a longer wavelength will be reflected within 10 or 20 picoseconds. This is useful for dispersion compensation. If you put this fiber grating into an optical communication circuit that suffered dispersion during its transmission, and you arranged that this delay spectrum was the opposite of the delay that occurred in the long distance of the fiber, you could compensate for the dispersion. So that's another reason why people sometimes chirp gratings. So I think now is a good time to take a little break. Give us a chance to read some of your questions, and Brian would like to ask you a few questions too. So please take it away, Brian.
Okay, so we just popped up the second poll for you guys. If you could please go ahead and answer that. In the meantime, Steve's going to be reading through the questions. So if you have questions, please go ahead and type them now into the questions section of the GoToWebinar interface. And just a reminder, you can go ahead and register for as many sessions as you'd like. We're going to be doing webinars all week. And as I suggested earlier, if you wanted to get the recording of this session ahead of time, it will go live in about an hour and a half on the website. You basically just go to the registration link that you used to originally sign up. You have to click the register button again with the same information, and then you'll be taken straight to the video recording. Okay, I'm going to go ahead and close the poll down now and pass it back to Steve for any questions that he'd like to answer.
Thank you, Brian. I have a question from Ruben. He asks, what does DHD/N mean in Grating Manager? Good question. It was found here, NH. Okay. The reason for this is that Optigrading does different kinds of gratings. What I'm showing you is a volume grating. This is where the grating is achieved by changing the refractive index of the core of an optical fiber. But Optigrading can do different kinds of gratings. It can also do a single waveguide, like a planar waveguide type of grating. And in this case, the grating is just a film on top of a substrate. And when we're doing a grating like this, there's more than one way to obtain the grating. We might obtain the grating by modulating the refractive index of the film, but we could also put an etching on the surface of the film. And in that case, if the grating is to be achieved by simply etching grooves in the surface of the film, we would select surface grating, and then the modulation would be not a refractive index but a height in microns. But at this point in the grating, when we're at the grading manager point, it doesn't know whether we're dealing with a fiber or a waveguide grading, so it doesn't really know whether to say this is a modulation in refractive index or a modulation in H, but it displays the number anyway. So what you've noticed is just a tiny bit of awkwardness in the interface. Good eyes, good eyes. Okay. What else have we got here? We have another question asking what the application of Optigrading can be used. Well, it can be used in any place where you have a waveguide that is a fiber or a planar waveguide. You want to use a grading to create some kind of spectrum, either transmission or reflection. It can be used in any circumstance in which you'd like to make designs like that. And what people choose to apply that to, goodness knows. I wouldn't be able to say. I did mention the application of dispersion compensation because that's well known to me. But it's not always known to me exactly what people are doing with these things. I do appreciate it when they tell me, but they don't always do that. All right, back to the application of dispersion compensation. I was part way through having designed a chirped grading, and I did notice that because it's got a delay spectrum like this, maybe that could be used as for dispersion compensation. But with the remaining time, what I'd like to do is just show you a few more features about Optigrading that will help with calculation and design. So I can do this. I did mention that we can trace the curves, and I was pointing out that we've got two. I did find the band edges. One feature I could show is that you can open more than one window at a time. So this might be of use because maybe in this window you'd like to remind yourself where the band edge was. It was at, well, the middle of the band is at 1.55. But what I'd like to show you in the other window is that Optigrading can calculate not just spectrum, it can also calculate a propagation picture. So now the axis is not wavelength. This is the actual length along the grating, which you might recall it was 10 millimeters long. So that's one end of the grating, that's the other. And what we're looking at right now is optical waves. That's the reflected one, and that's the transmitted one. And the reflected one, they have the same amplitude. Let me put more propagation steps in that, make it look better. People sometimes ask me, why is it that this curve can be greater than 1? And the answer is that we're not actually looking at power here. What is being displayed are two waves. The wave of the blue curve is the amplitude of the waves going from right to left. and the display of the red curve is the amplitude of the waves going from left to right. Well, this is what's happening at the center wavelength when we have total reflection. That's why the amplitude of the reflected wave is the same as the amplitude of the incident wave. The wave going from left to right has the same amplitude as the wave going from right to left. But it's not unusual in the middle or somewhere inside a Bragg grating to have some resonance occurring. These resonances are the same thing as you would get in a Fabry-Perot resonator. They occur because there's high reflectance material on both sides. And when you get constructive interference, you can get amplitudes larger than 1 from this. This is what happens at the center wavelength. And maybe recall that it's interesting to see what happens at one of the edges. At 1.548, we're at the lower end of the spectrum. So let's see what happens at 1.548. This is sort of the shorter wavelength. So here we get very good reflection again, but it looks like the wave is penetrating much more deeply into the into the grating at this point. And this still has the same delay spectrum. I'm going to open a few more windows here to make the picture even busier, but maybe also more informative in the end, you'll see. And if I tile these, okay, I'm going to open 2, 3, 4, I want to open 1. Okay, and if I tile these, they come in. So here we have the same grating, just viewed in a bunch of different ways at the same time. In this one, I'm going to show our profile. And this one is showing the delay spectrum. And remember that we did have high reflectivity throughout all of that band. This shows the propagation at 1.548. This is the propagation at 1.548, so that's about there at this end of the low end, at the short wavelength end of the passband. Let's have a look at the propagation picture at the other end, 1.552. And at this wavelength, at 1.552 is about here, it looks like the wave does not penetrate very deeply into the grating at all. And looking at the design of the grating, this isn't too surprising, because at a long wavelength, 1.552, when the light comes in the left side, it will encounter periods with a length that are closely matching the quarter wave Bragg condition of the longer wavelength light. And almost all of this light gets turned around early on. On the other hand, the short wavelength light, which is at 1.548, It doesn't see a Bragg condition when it comes in here because the period is too long for it. And it sails through most of the grading unimpeded for the most part until it reaches the far end of the grading where it finds shorter periods. And at this point, it reaches a Bragg condition and turns around. That's where this picture comes from on the bottom right. So this gives a clue about the mechanism for this delay spectrum. It does help to explain why the delay is long for short wavelengths and the delay is short for long wavelength light. And it even works out quantitatively. The difference in the delay at the two ends, we have a tracing, I already showed you the tracing function, but if you do the tracing function, you'll find that it's about 60 picoseconds shift from, it's 60 picoseconds longer at the short wavelengths than it is at the long wavelengths. So let's have a look at the experience. The long wavelengths, they turn around at about 7.5 millimeters. So it means that the long wavelength light travels about 15 millimeters in going from where it starts the grading until it turns around and comes back. The long wavelength light, on the other hand, turns around within a millimeter. It doesn't travel much more than a millimeter. And so it means that the difference in travel time of short wavelength to long wavelength, the short wavelengths are going about 12 millimeters farther than the long wavelengths. Well, how long does it take light to move 12 millimeters? I'll get out my calculator. Speed of light, it's approximately 0.3 millimeters per picosecond. But this is a guided wave, and so it's traveling on the fiber, and which slows the wave down by the modal index. So instead of having 0.3 millimeters per picosecond, we're only going to have about it's going to be about 40% shorter than that because the modal index is about 1.4. So we actually have a speed, the wave is actually traveling at about 0.2 millimeters per second. And that means that about 4.6 millimeter, about 4.6 picoseconds pass for every millimeter of travel. And the difference in travel time between the short and long wavelengths was about 12 millimeters. So yeah, 56 picoseconds, and we do see about 60 picoseconds shift here. So in this grading, the mechanism for the dispersion compensation for the change in delay over different wavelengths, it's largely explained by travel times, that a short wavelength just spends more time in the grading and travels a greater distance before turning around. Yeah. Okay. That's about the all I wanted to show you of all I have time to show you of OptiGrating today. And so now I would like to say goodbye, and I will pass you back to Brian, who will say a few goodbyes for us. Thank you, Brian.
Okay, so we're gonna go ahead and just pop up the last poll. We do have a couple questions that came in. I'll let Steve take some time to go ahead and read those. Again, if we can't answer your questions right now, we're gonna get back to everybody via email afterwards. Yeah, so that's if you have any questions, feel free to ask them right now. I mean, Steve's the expert on the topics, so right now you have his full attention. And if you want to register for any other sessions, I put the link in the chat window. Again, you can find out who the winner of the gift card is at about 20 minutes from now. The recording should go up in about an hour from right now. Otherwise, I'll hand it back to Steve to see if you would like to answer any of the questions that you guys asked. I think that that Steve might have already left the session. So any questions that were remaining, we'll go ahead and answer those via email. Thank you guys for attending, and feel free to register for as many sessions as you'd like. Goodbye.